welcome to the statics tutorials. So with this problem, we have a spool that has a rope wound around this inside radius of 0.2 meters, but the spool has an outer radius of 0.3 meters. The spool is resting against a rough surface here at A and a rough surface here at B. We have identical coefficients of static friction of 0.102 and identical coefficients of kinetic friction of 0.0914 at both A and B. So we want to find the smallest force F to cause impending motion in our system. Here's our free body diagram. We have our 25 kilogram mass times 9.81 right at the center of gravity. We have the force acting up, F. We have a normal force from the contact with the surface at B, and we have a normal force from the contact at the surface at A. If we're going to pull up on it in F, it's going to cause a tendency for it to rotate in this direction, and so friction is going to oppose that relative motion, and we'll have a friction force in B going in this direction and a friction force in A going in this direction. If we're going to have impending motion, we're going to have impending motion at both A and B. It has to slip at both locations. And so we can say that FA is equal to the coefficient of static friction times NA, and FB is equal to the coefficient of static friction times NB. Notice that we're using the static coefficient of friction because we're looking at impending motion. It's still static. We haven't broken past that into the kinetic regime yet. Here's the sum of forces in the y direction. So we have FA, we have NB here, we have positive F, and then we have the negative weight of 245 newtons. Then we can do sum of forces in the x direction. So we'll have NA, and then we'll have negative FB. Remember though, FB is equal to that coefficient of friction, the 0.102 times the normal force at B. So we can go ahead and make that substitution into the sum of forces in the x direction, and then divide through by the 0.102, and we'll get NB is equal to 9.80 NA. Then we can do our sum of moments, and really there's several points that we could do sum of moments about. We could do sum of moments about the center of gravity and get there. We could do sum of moments about B, or we could do sum of moments about A, and those would all give us good equations that we could use to solve this problem. But for this example, I just did B. So we have the force, frictional force at A. Remember that that's 0.102 coefficient of friction times NA times the overall radius of 0.3 meters. That's going to give you a negative moment about B here. You've got the normal force at A that's up 1 radius. So you've got a negative moment, 0.3, the 1 radius times the NA here. And then you have FA. FA is going to be over just the smaller radius, so the 0.2 meters. The center of gravity, the weight at the center of gravity is going to go through B, so it won't contribute a moment. And then, of course, if we do the moment at B, the two forces at B don't show up in that moment. Looking at this equation, now we can write F as a function of NA just by combining the terms. Going back to our sum of forces in the y then, we can substitute out FA, write it as 0.102 NA, carry the other terms through. Where we had F, let's go ahead and make this substitution. Where we had NB, let's go ahead and make that substitution. Then everything in this equation is either a constant term like the 245, or it's a function of NA. So we can solve this equation, one unknown, one equation for NA, get that value, and then take that value for NA and plug it right back up in here and solve for the F, and we'll get that the smallest force is 35.1 newtons. Thanks for watching.